Good evening, everyone. I'm Anesh Ambekar, PMRF and PhD candidate from Aerospace Engineering, ISC Bengaluru. Welcome to this week's live interaction session for the NPTEL course Dynamic Behavior of Materials. The course code is NOC 24ME102. This week we'll be going through the week 6 content, specifically that covers impact shock wave under impact between two plates, how we use that to experimentally determine an equation of state, then differences between an ideal and a real shock wave profile, theoretical approach to equation of state, particularly the Mie-Brunessaw equation, and then an extension to mixtures as well as powdered materials. So impact of plates. So shock waves are generated when two plates impact together at very high speeds. For us to analyze it, we consider three necessary conditions. I'll draw the two plates. So P refers to projectile. It is moving with a velocity v, and T refers to target. It is stationary, and my observer is somewhere here. This is T less than 0. We have three conditions here which will help us analyze this model this phenomena, as well as these three conditions are important in generation of shock waves in practical cases. Those are planar, which means that flat plates. Second is, I should write this in impact conditions. Second is parallel, which means all points in contact simultaneously, same time. And third, normal. This means that projectile velocity, so projectile P velocity, which is V, is parallel to, or I should write this, perpendicular to the planar surface of P. With the parallelity condition, that becomes, it's also perpendicular to the target T. At t less than 0, we can see that the projectile P is rushing towards the target T with a fixed velocity V. At t equal to 0, we'll consider it to be impact. Something will start happening on the surface. This is t equal to 0, which is impact. And at t greater than 0, you have maybe the surface is slightly shifted downwards, and you have shock regions developed in both projectile and target. Both projectile and target will have shock waves, which will move shock waves. So the shock front will move with some velocity us, and the particles will move with velocity say up projectile and u particle target. This is still moving with velocity v. Right. So uh, while analyzing what happens at the contact surface, we'll consider two important points. First is interface constraints or conditions. First is both the projectile and target at the interface, they'll have the same displacement so that the contact remains. If suppose the projectile moves with a higher velocity, and or if suppose the target moves with a higher velocity at the impact surface, you will see the target and projectile starting to separate slowly. Whereas if the other way around, if the projectile surface, impact surface has a higher speed compared to target surface, we'll see the projectile material to start indenting into the target surface. So both of these conditions are undesirable because they'll either end up creating voids on the surface or high density regions. So in simple terms, we have same, or rather I should write displacement, and therefore velocity continuity at the interface. The second condition is, suppose their second condition relates to the force. So if there is a force mismatch on the surface, you'll have a pressure mismatch. That pressure mismatch will create two different shock waves in the material. So you'll see, like, or rather two different waves coming out in the material. Here we are assuming only one shock front in both projectile and target, so that would require the force along the surface to be constant in both projectile as well as target. Sorry, not constant. Force in both the projectile and the target at the impact surface should match. They should have equal magnitude. So that would lead to them having same pressure along the impact surface. Force, therefore pressure matching at the interface. If displacement continuity is not satisfied, we'll otherwise end up with, we'll have either voids or high density region. And if the pressure matching condition is not satisfied, we'll have two, uh, you'll have basically otherwise multiple wavefronts. So we only are taking the case of a single wavefront. Later on, when we go, I think in week 8 or so, when we go into phase transformations, we'll see how you have like two different uh, shock fronts coming up. So with these conditions, we'll now move to the mathematics. So I'll write, okay, we have projectile P, we have target T, and we'll write down the basic equations. First is, if we take momentum conservation, we can also write down similarly your mass conservation equations by taking a small control volume before and after the shock front, as we have done in the previous week's lecture, like a small control volume like this. Some material flows in and some material flows out, and that mass should be balanced. So that is reflected in shock wave front velocity, particle velocity, as well as initial rest density and shock material density. Now we'll directly move on to the momentum conservation equation. We have also seen that previously. That is, so assuming no initial pressure in the shock free zone. Assume one is this and another is shock free zone. This is region ahead of the shock. Initially at rest. So there was no particle velocity. There is no particle velocity or pressure component ahead of the shock front. So as the shock front moves forward, you'll have this relation between pressure and P is rho naught U shock U particle. This is P target is rho naught target U shock target U particle of target. Right. So this is the first condition, first equation. Second equation is equation of state. So we'll assume a linear relationship between shock wave velocity and particle velocity. We have already seen this form as U shock particle is C particle plus S particle U particle of projectile, and U shock target is C target plus S target U particle of target. If you combine these two equations, you end up with P particle is P projectile is rho naught projectile C projectile plus SP into UP projectile into UP projectile. And P target is rho naught target C target plus S target into UP target into UP target. Okay, so this has the pressure. So now we make use of the interface condition. Condition 1 gives us that the velocity at the interface has to be the same. So if we look in the projectile, that velocity would be going downwards with V minus UP particle, and for the target, velocity would be UP target. So first condition gives us V minus UP projectile is equal to UP target, right? And which gives us, and the second condition, substituting first into these equations, second condition is P projectile is P target, which gives rho naught projectile C projectile plus SP into UPP. UPP is rho naught T CT plus ST into V minus UPP to V minus UPP. If I simplify this, I have rho naught projectile CP UPP plus rho naught projectile SP to UPP square is equal to rho naught CT V minus rho naught T CT UPP plus rho naught T ST V minus UPP whole square would be V square minus 2V UPP plus UPP whole square. So it's basically a quadratic equation in UP particle. So you have what rho naught T CP UPP plus rho naught T ST UPP square is equal to, I'll take the constant terms out. So rho naught T CT rho naught T V CT plus ST V rho naught CT rho naught V plus rho naught T ST UPP square minus 2 rho naught T ST V into UPP. So this is basically a quadratic equation in UPP, which we can use to solve the, which we can use to get solutions of UPP, which can then be used to evaluate UPT, and these two can then be used to evaluate PP is equal to PT is equal to P star. Okay, so this is the algebraic way. There is also a graphical way to do this. If I plot the pressure versus particle velocity plot, then I have initially that and I just plot this say the right hand side equation. I'll label point as V. The target pressure will go something like this. This is target. Whereas the part, whereas the projectile pressure will go something like this. These two curves will thus intersect at a point PP is equal to PT P star. That will give you velocity. One component will be UP particle, the other component will be UP target. So if we look at an example of the same, suppose you have a copper plate impacting with a velocity of 300 meter per second, say 500 meter per second on an iron plate. So, and my target copper is my projectile. So I have V is equal to 500 meter per second. Then for copper, my equation of state is use S is equal to 3.94 or 3940 plus 1.49 UP meter per second. And for iron, it is 3570 plus 1.90 UP meter per second. So if this is what we have, then I can write the projectile pressure, and my densities are for iron it is for copper is 9.8940 kg per meter cube. For iron, if I take the cast iron density, that would be 7760 kg per meter. Okay, so then if I now write my equations, my projectile pressure is 8940 into yes, 3940 plus 1.49 V minus, suppose this has some particle, this will have some particle velocity UP. V is 500, so 500 minus UP into 500 minus UP, and my target pressure would be 7160. I'll replace this with X. X is UP in iron, which is my target. 3570 plus 1.9 X into X. So this is how the equations look like, and then we can simplify it. 940 by 7760, 3940 into 500 minus x plus 1.49 into 500 minus x whole square is equal to 3570x plus 1.90 x square. I simplify this, I end up with 1.15 into 3947. So 4531 500 minus x plus 1.15 into 1.49 is 1.71 500 minus x whole square 3570 x 1.90 x square. 31 into 500 is 2.26. I'm simplifying it a bit. 2.26 10 raised to 6 minus 4531 x plus 2.427 10 raised to 6 71 into minus 1710x plus 1.71 square is equal to 3570x plus 1.90 x square. So we can simplify this. So it's 0.19 x square and we got 3570 plus 1710 plus 4531 plus 9811x and minus 2.26 plus 0.427. 2.26 is plus 0.427. That is 2687000. Roughly, I've made some approximation, but roughly this is how it would look like. Should give us is equal to minus 9811 plus under root of p square, so 98 square. We are only taking the plus sign because if we take the minus sign, then the square root part is already greater than 9811, which would cause a negative velocity. So that would mean that if the impact happens, then we are saying that our target will move in the opposite direction. 0.126, which should look something like 4 into 0.19 into 6, 7, 0, 0, 0, 4 plus 9, 9, 6, 2, 5, 7, so 9, 9, plus 204, 2, and 20. Square root of just a second, 965, 721 plus 20 42120. Square root of this is 9914. So you have 9914 minus 9811, which is 103. 4 minus 98, which is 103. And then you have 103 by 0.38 is equal to 3 divided by 0.3 is equal to 271. Is equal to x. So which means that if the copper plate impacts at 500 meter per second, this is my copper plate, iron T less than 0, this is at rest, then you would have shock shock wave generated in both, and here the particle velocity UP would be around 271 meter per second. It's a sufficiently it's a pretty high particle velocity, but uh, I think if I made a mistake in the calculation, I'm not sure, but this is what it seems to be. Okay, but apart from solving this kind of an equation, this parallel plate impact and shock waves being generated is useful in another way to help us determine experimentally what the equation of state looks like. So, as we have already seen, you have got like 5 parameters in the shock wave and 3 conservation equations, these being mass, momentum, and energy. So we add add EOS to this mixture to get a locus of all shock points based on some initial state, say P naught, V naught, and so on. Right. So this equation of state is fundamentally important in that sense. And to evaluate it, we have a few experimental methods. I think in lecture we already discussed one of the older methods where you have something like a high energy explosive and then an explosive lens which takes away energy in different directions at different speed, and then you measure uh, particle velocities at different locations, and that gives you a relationship between pressure and particle velocity. What we wish to do here is to use the concept of parallel plate impact resulting in shock waves to arrive at an estimated equation of state. So how we do this? We use a gas gun and have a projectile or a sapper. So you have got gun barrel, sabber, which is your projectile, is moving with a velocity v. Ahead of it, you have a parallel. You have plate, the first plate, which is our projectile. You have 3 or more small velocity pins. These are used to estimate what the impact velocity v looks like, and then you have a target t, right? So for this target, you have got 2 pins on the free surface. Okay, so how do we proceed here? So v is basically your impact velocity. From the previous experiment, we have already seen. From this analysis, we have already seen a projectile P with a velocity v impacting a target T, which was initially at rest. In this case, for the experimental part, v becomes your impact velocity. So it is determined known using velocity pins on the bottom of the barrel. Next, you have projectile P. So it's projectile. EOS is known. So one equation of state is known, and we have to determine what happens to the next one. Third is you have got pins, these pins, right? These are used to determine free surface particle velocity. I think a couple of lectures ago we all have already discussed that if you have particle velocity, or rather V free surface, particle velocity at free surface is nothing but twice of UP. We have already discussed that. This is because when an incident wave hits a free surface, there is also a release wave coming out of it. But in both of the cases, particle velocity sense is same. So your when those two waves come together, they at the free surface they come together in the same phase, resulting in twice as much as particle velocity as you would see in the incident wave. So because we are measuring it at free surface, this is an important thing to notice that whatever velocity we get is actually twice of your uh, particle velocity due to only the incident wave. Next T is the target with unknown EOS. So we'll try to establish a pressure in the particle velocity relationship. So we need only one more relationship for the target. We already have mass, momentum, and energy conservation equation. So we are looking at the pressure and particle velocity equation. So initially what we do is that the sabo hits the target with some velocity v1, v2, v3. It can be controlled well because it's a gas gun, so we can adjust the pressure of the gas released behind the suburb, and that would in turn lead to different velocities. Suppose we start with a velocity v1, then you would have impact velocity v1. We have another again impacted with some velocity v2. We again impacted with velocity v3. Okay, so these are all for projectile P. Next, what we do is we make use of Rayleigh lines, wherein if you remember the equation, you have momentum conservation equation. This basically forms a slope between particle velocity and pressure. So because we already know what rho naught P looks like, we also know what USP looks like, the shock wave velocity looks like for your projectile. We can evaluate what is the exact pressure being generated. So this is rho naught. So I should talk about target UST PT. We know the rho naught T, which is the initial density or like the free density. Sorry, shock free like resting material density. We can also measure the shock wave velocity. We have pins at the start and end, at the beginning and end of the surface of the target. So using this, we can determine how much time the shock front takes to move from say left of the target to right of the target. This is different from the actual particle velocity. So note the distinction. Actual particle velocity would refer to at that cross section how the particle will move, whereas shock wave velocity is only like the shock front traveling from say left surface or left boundary of the target to the right boundary of the target. We construct these Rayleigh lines. So ST1. Similarly, this is your rho naught TUST2, where those Rayleigh lines will cut into your pressure and particle velocity lines for target. That would form the common pressure. Like we have already seen, P star is equal to pressure pressure at the interface on both target and projectile should match. So wherein those lines cut, that is the pressure that they reach. Rho naught T UST. So this gives us 3 points. From this we could estimate a equation of state looking like this. Right. So once this line is drawn, the target T profile becomes known. And then you can use this equation along with your above three questions to calculate all the different locus of all the different points of the shock state. Okay. Next part is about a small brief on the shock wave profile. Yes, go on.
Yes, sir. Sir,
Hmm.
actually, how to find the slope of the radial lines? Because in previous discussion,
Hmm.
we find that slope is rho naught square US square, but here we just find with the rho with the US calculation. So how do we calculate
No,
that,
I
sir?
think that rho naught square US square is not a plot between pressure and particle velocity. Just let me once check. I think that is between pressure and specific volume.
So volume, yeah, yes, sir.
Hmm. So here we are interested in evaluating pressure and sorry particle velocity.
Hmm.
Uh, that is the equation that we are using here, and we already know what the target density looks like, and we know the time of arrival between the left and right boundaries for the shock front to move. That would give us an estimate of the shock front velocity inside the target.
Okay, here we can use just a impedance, shock impedance as a slope of the rate decline,
Yes,
right, sir?
yes, yes, yes.
Oh, okay,
So
okay,
this
sir.
is the
Thank you.
plot between
Okay,
sorry,
okay, sir.
pressure and particle velocity.
Okay, sir.
Okay. Next part, profile of a shock wave. So suppose I'm looking at location X, the wave is passing through. Ideal profile would look something like this is ideal. There is a very steep shock front. We have already seen that this steepening happens because as the pressure increases, your velocity, your wave velocity will also increase, and then that would cause like steepening of the wave front. That is ideally that would be like a very straight line. So suppose this is velocity versus time, or it could equivalent be also between stress versus time at the location X. This is my steep shock front. Then there is a duration of pulse. Then there is release. So release, steep front, pulse duration. Right. So this is how the ideal profile looks like, but in reality we have a different version which looks something like this. So again, sigma u versus time. Initially, there is a rapid increase of say stress till it reaches an elastic limit. which is called as HEL, Huguenot elastic limit. And there is a plastic flow and material rises as per the plastic modulus. Sometimes there will be phase transformation that is more distinct. So this would be phase transformation. A little amount of time would be rather not little, rather a relatively noticeable amount. It will happen very fast, but it will still be relatively noticeable. A small but relatively noticeable amount of time will be involved in the phase transformation process. After which it reaches your Huguenot state, following which there is a high there is an elastic release. So I'll write it as high pressure elasticity. Some cyclic loading dissipation. Finally, yes. So if you are putting a compressive wave inside, if you are putting a compressive wave inside the material with a very high pressure, typically we'll have velocity pins on say like the other end, which would be a free surface. Once the wave hits the free surface, it will a release wave, tensile wave would come out, and that can lead to spalling, which can also be seen, which may be seen sometimes. Another point is that I am taking this distinction between Huguenot, like the HEL and the plastic modulus, elastic and the plastic regions. This may not be so distinct. Usually, actually, it's usually not very distinct. Even in tensile tests, also it's hard to determine where exactly the yield point is. So there are some methods, some mathematical approaches, as well as some cutoffs which we normally use. So here I am showing like some region, but it may be like this may be very flat, something like this. But it's not very noticeable. Okay, so different regions. I'll just quickly walk through them. First is your pressure increases quickly in the elastic region till you cannot elastic limit. Then material deformation as per plastic regime. Both of these are based on your constitutive laws, and then you could have phase transformation if it exists. Again, we'll look into conditions for phase transformation in detail for the next few classes. Here, one important thing that happens is this leads to separation of waves. So you can have like two shock waves, two wave fronts coming up, usually clearly seen. It's two waves. Then you have a plateau for pulse duration. So actually this figure on the left is a bit misleading. So this whole thing happens very quickly. Then you would normally have a pulse duration which is sufficiently larger than the left loading part that I have shown. I've shown them to be equal, but that may not be the case. And your unloading is initially elastic and then plastic. There may be some cyclic loading, unloading in the plastic when it's moving down in the unloading region. Sorry, in the plastic region when it's unloading, there may be some cyclic loading, unloading that could result into some dissipation. Again, that's a separate topic. And finally, you could have so like this is obtained using VISAR technique. So in VISAR, you have velocity measurement on free surface, which leads to wave reflection, which can lead to spalling. Again, spalling will be treated later on in more detail, but rough idea is that compressive wave hits the free surface due to force balance. There will be a tensile release wave coming out, and suppose there are some uh, sorry, suppose there are some small voids or some features that you have machined into your component, then that basically leads to a tensile loading. So, like think of it like if there are small microscopic voids or cracks inside the material, and that this tensile pulse, release pulse, which is coming from the free surface, can lead to fracture. In worst cases, that would be leading into spalling. Okay. So the next part is on theoretical approaches for equation of states. Particularly, we'll be looking at the Mi-Grunesa approach. I'll just write MG for short, MG equation of state for short. Moving forward, so this is basically derived from first principles, but it has been shown to predict like uh, for not only say metals but also very well for powdered materials, which we'll be looking at the end. And how this works is, so I presume most of you have a little bit of understanding of how, suppose you have two atoms or more, right? Suppose you have large number of atoms. When these atoms come close together, their electron shells will start interpenetrating, and as a result, they'll start repulsing each other. That will lead to an increase in potential energy. Similarly, when they are too far away, the atoms can act like there will be some mutual forces of attraction. So, like, could be van der Waals, I think, that would try to bring them. There will be cohesive forces which will try to bring them together. So, there is a dance between these two forces that leads to us having a plot of energy versus distance which goes like this. This is the repulsive part on the left, and on the right you have the attractive cohesive forces. I think this is given by Condon and Morse. Calculated from first principles at 0 Kelvin. So for only two atoms. From this you can evaluate force is equal to minus partial derivative of potential energy with respect to displacement. If I draw force versus distance plot, you have this is repulsion, this is attraction, this is minimum energy state. So normally this is where like this is the interatomic distance for which where you may expect to find the atoms. We can further use this plot to try and create a pressure versus volume plot. So one of the most simplest approaches you can think about this is as I move from as I decrease the interatomic distance from minimum energy state, you can think of the atoms to have say like spheres with radius r, and they'll start compressing. And if we assume that the compression, sorry, not assume, the compression will be uniform. So the interatomic distance say goes from A to say A minus delta. Radius of the atomic sphere will thus go from say A by 2 to A minus delta by 2. So there is a shrinking in volume, and because of the force, you can estimate that there will be some sort of pressure depending on what your current surface area looks like. So if I draw pressure versus volume curve, would look this is say the base volume. It would look something like this. An important thing to note here is that as volume decreases, your magnitude of pressure versus volume increases. So from the Condon-Morse curve, we are able to see this dP by dV increase as V decreases, which is an important condition. We have already seen this, necessary for shock waves. If suppose the relation is other way around, dP by dV decreases, then you can expect the instead of thinning of the shock front, you can expect widening of the wave front. So that would be dispersion. So from this energy versus distance plot, we are able to get pressure versus volume, and we also get the necessary condition for the shock wave. And part of it was developed by me, and then it was refined by Karunesa. So it basically uses statistical mechanics and it's important in as it finds EOS for powdered materials as well. So this derivation is a little tricky. So I thought I'll try to include it in full in this lecture. So we'll first consider only one atom. So an atom, it is a 3 degree of freedom oscillator. So along X, Y, and Z. And you can have your energy, or sorry, oscillators. You can have like 3 degree of freedom oscillators. Can have different natural frequency. So how the atom say oscillates along X? It can have some frequency nu one, along Y it can have a frequency nu two, and so on. Right. So each of these acts like an oscillator. And if I now have to evaluate energy of one atom, there is a component of ground state energy, and with some with some frequency nu, half h nu, this is ground state, and there will be summation ni h nu I is equal to 1 to 3. This ni refers to nth level oscillator. So you have like different natural frequencies. So each natural frequency will have So depending on whether it's on, say, like the first natural frequency or second or third, different integer. These are all integers. Positive, right? And this h nu refers to energy of the, together this term nh nu refers to energy of the oscillator with ni comma nu I. Nu I being the frequency and ni being which natural frequency, which level of oscillator you have. If we consider this only this one oscillator, its probability only one oscillator. So each each atom has each atom is a 3 degree of freedom oscillator. Out of that, now we are looking at only one. So suppose along x for the sake of argument. So we have this relation where probability of the oscillator, probability of oscillator being with energy epsilon I. This is given as EI is proportional to GI e raised to minus epsilon I by kT. Again, kT constants, GI refers to something called as degeneracy, which you can think of in a simplified manner as number of different states to achieve same energy epsilon I. Right, so if I write the probability of the ith oscillator to have energy epsilon I, that would be simply summing up like this fractional probability for this particular event and then summing up probabilities for or all the other events. So that would be say gi e raised to minus epsilon I by kt on summation over j gj e raised to minus epsilon j by kt. So all possible states in the denominator. Therefore, if I take the mean energy of this single oscillator, again single oscillator, single degree of freedom, not three, that would be summation over I, pi of epsilon I. So all the possible states epsilon I, energy states wherein that oscillator can exist, multiplied by its probability, which would be summation over I, epsilon I, gi e raised to minus epsilon I by kt upon summation over j gj e raised to minus epsilon j by kt. Again, we can interchange. So this I and j are all spanning over all states. I can write, say, the denominator as a summation of I again, just to remove any confusion. So what we do is we first this this right. So this summation term that we have in the denominator, right? I'll can rewrite this as d upon d of 1 by kt log of summation over j or summation over I, either would work, e raised to minus epsilon I by kt. So taking derivative, you can see that this minus epsilon derivative with respect to 1 by kt, you can see that this minus epsilon I would come into the summation, and this whole summation over all I would go into denominator. So this term would be obtained, and after derivative, this term would be obtained. Okay, right. So now we make one assumption. So assuming no degeneracy. So by what do we mean by no degeneracy? We say that the energy epsilon I can be achieved by the oscillator exactly one way. So there are no, like, say, 1, 2, 10, 15 ways to achieve the same energy. So each energy level epsilon I, suppose epsilon 1, epsilon 2, epsilon 3, they are all distinct and can be only achieved by a single frequency and the associated oscillator level. So if we do this, we get Gi is equal to 1, which is nothing but I'll write this whole thing as F. F I'll call as partition function. Partition function, so my F becomes summation over I e raised to minus epsilon I by kt, and epsilon I we know is nothing but summation over I e raised to minus I h nu by kt. So epsilon I am replacing by n into h nu, and that gives me F is equal to summation over I e raised to minus I h nu by kt, which is basically a geometric progression series 1 upon 1 minus to minus h nu by kt. So this is how the partition function would look like for one single oscillator. Now, if we take mean energy of one oscillator, that would be E bar is equal to, so, so again we'll do this summation thing, and you have this minus d by t of 1 by kt ln of 1 over 1 minus e raised to minus h nu by kt. Right, so 1 by log of 1 by is would be nothing but minus log is, so that minus minus sign would cancel out, and you would end up with 1 over 1 minus e raised to minus h nu by kt h nu is to minus h nu by kt, but nothing but h nu upon e raised to h nu by kt minus 1. So this would be the mean energy of one oscillator in a system with n capital N atoms. You would have mean energy, or rather now because we have large number, suppose n is greater than n is very large. If n is very large, what that would mean is whatever we calculate the mean energy to be, that would be, because n is so large, that that mean would be essentially what energy we expected the overall system to be. That would be a sum of some potential function plus summation I is equal to 1 to 3n half of h nu I, which is my ground state energy, plus nu I is I'm writing for each oscillator, summation I is equal to 1 to 3n h nu I by e raised to h nu I by kt minus 1. So mean energy of one oscillator with its uh, associated frequency, ground state, and the potential energy term. So this P is the potential energy term. And I'll now write down Helmholtz free energy for one oscillator. Again, these terms are a bit complex, so I think it might be I'm doing more the mathematical uh, derivation based on some assumed equation forms. It might be a good idea if you are interested. It might be a good idea to look into a bit of statistical mechanics and thermodynamics to see how they two link together. So, if I'm now writing the Helmholtz free energy for one oscillator, that would be minus kT ln of f, where f is the partition function, minus kT ln of, sorry, kT ln of 1 minus h nu by kT, ln of 1 by that minus will come out. Then, if we have this as my Helmholtz energy, then my pressure definition would become change in the Helmholtz energy with respect to volume, negative of change in Helmholtz free energy with respect to volume at a given temperature, so isotherm. So this is for one oscillator. If we write it for the system, we'll have to include the potential energy as well as the ground state terms. A bar becomes P plus summation I is equal to 1 to 3n half h nu I plus kT summation 1 to 3n. So ground energy term, potential energy term, ground energy term, and then our definition, which is log of 1 minus e raised to minus h nu I by kT. And pressure for the overall system. And then pressure in the system becomes P is minus dou A by dou V T, which is minus dou d phi by dV. Now this is the tricky part, 1 by V summation. So instead of doing d by dV, instead of doing dou by dou V, we do sorry, we do this is volume, we do it as dou by dou V is gamma dou by dou nu at t, where gamma is minus V by minus dou by dou V is minus V by nu I dou nu I by dou t at t. This is gamma I, which is nothing but minus partial derivative of log of nu I, partial derivative of log of volume V at constant temperature. So instead of using this term, we will be using this term, and we have a constant gamma I defined as follows. Summation 1 to 3n over gamma I times half h nu I plus nu I by kT into minus h e raised to minus h nu I by kT, like kT into kT into e raised to minus h nu I by kT. So you end up with minus dp by dv, 1 by v, I is equal to 1 to 3 n gamma I to this term. Right. If we assume gamma I is equal to gamma for all I is equal to 1 to 3n. So we assume like this gamma constant to be same throughout all the oscillators, all 3n oscillators. This gamma term can come out and you end up with P is equal to minus d phi by dv plus 1 by v into gamma summation I is equal to 1 to 3n half h nu I plus this kt went inside here plus h nu I upon e raised to h nu I by kt minus 1. This whole thing, this whole thing is the internal energy associated with like the overall system. And since we are initially calculating it at 0 Kelvin, our pressure 0 Kelvin is minus d phi by dv gamma by v 0 Kelvin. This equation we extended to a different state. So you go from P 0 Kelvin, E 0 Kelvin. There will be some V 0 Kelvin also associated with. And if we now send this equation to another state with values P, V, and D, and we see that this d phi by dv term can be constant. So you have P minus P 0 Kelvin, gamma by V, E minus E 0. So this equation can be alternately used to relate PE to pH, EH on the UV naught curve. So this is the Mie-Gronessa equation of state. Uh, you can like the form of equation has been extended. P is equal to minus d phi by dv plus gamma by v e. That has been extended to two different states, and together we basically match them. Here the condition is at same volume v, which the same volume v condition would be important in the porous material section. From this we can write this as small change in pressure and written as gamma by V, small change in internal energy, which means gamma is V times the partial derivative of P with respect to E at constant specific volume. Now we do some mathematical jugglery between thermodynamic states, thermodynamic state variables. So you have dou P by dou E at V equaling dou P by dou T at constant volume into dou T by dou E at constant volume. This we know that change in internal energy with respect to temperature is nothing but your CV, coefficient of volumetric, uh, sorry, constant, not isobaric, constant volume heat capacity CV. And another thing we could do with dou P by dou T at V is minus. So PV and T, pressure, volume, temperature would uniquely determine one point on one thermodynamic state. So we can juggle those variables around as V by dou V at T into dou V by dou T at T. Dou V by dou T of P looks similar to volumetric uh, expansion, volumetric thermal coefficient. So 1 by V dou V by dou T at T. This is volumetric thermal expansion. This is equal to 3 times alpha, where alpha is the linear coefficient of thermal expansion. And dou P by dou V, I write 1 by, minus 1 by V dou V by dou P. constant temperature. This is my isothermal compressibility. This is K, which putting this all together, you end up with an equation that looks like gamma is equal to gamma by V. Gamma by V is nothing but partial derivative of E with respect to V. So, and that if I put together all these terms, this looks like 3 alpha specific heat and isothermal compressibility. So this gives you a nice estimate. Another is an empirical relation. Gamma is approximately 2s minus 1. This is what has been observed for a lot of materials. Okay, from this you can say that if my parameters alpha, CV, and K are fairly constant, then whatever you have at say one state, that ratio gamma by V should be same as another state. If I look at an example, suppose copper. For copper, we know that CV is 376 joule per kg Kelvin. Alpha is 16.7 into 10 raised to minus 6 per Kelvin. Rho naught is 1 by V naught is 8930 kg per meter cube. And isothermal compressibility is kappa is 7.5 10 raised to minus 8. I have this in another unit, centimeter square per kg force. Okay, I have to convert this. So from this you can determine gamma naught is equal to V naught P alpha by VK 1 by 8930 3 16.7 10 raised to minus 6 upon 376 5 10 raised to minus 8 so minus 2. So check the next 1 second. Take this as 0.376 joule per gram. So the gram centimeter, this is 8.93 gram per cc. So you have got 1 over 8.93 into should be minus 1 upon 376. So compressibility 1 upon 7.5 10 raised to minus 8. So 3 alpha is 50.1 10 raised to minus 6 Kelvin inverse. So this ends up to be around 2.005. Yeah, almost 2. Okay, so we have already seen that for copper, S for copper is 1.49. So from this equation, gamma is 2 into 1.49 minus 1, which is 1.9. Again, approximately this value. Okay, hope this part is a little more clear than what we have seen in class. Hopefully, I have not added to more confusion. So I'll just recap. You have energy versus distance plot for each for two atoms. From that we can evaluate force distance, then pressure volume plots. Then we looked at a single atom as a 3 degree of freedom oscillator. Then we isolated one oscillator out of it. And I think this half h nu should be added to each oscillator. Okay. I made a mistake. Okay. Uh, so each oscillator will have some energy equal to n into h into nu, and that oscillator may exist in different states with different probability. So what we are interested in, why we are interested in the probability distribution. Another reason is that a system of atoms will have like a very large number of. You already know how big Avogadro's number is. So if you take like 1 mole of say a carbon, that would be like 6 gram. 1 mole of, sorry, 12 grams. Yeah, 12 grams. So in that you will have something like 10 raised to 23, 6 into 10 raised to 23 atoms. So the reason we are interested in probability distribution is because you have so many number of atoms. Eventually, once we sum up the energy of all those oscillators acting within all the three oscillators acting within each atom, they will eventually saturate to a mean. So that is why we are interested in the probability distribution. We took the case where there is no degeneracy, so each oscillator can only exist in one fixed state of energy, and that energy state can only be reached using one frequency, nu I or n nu I. So the nth energy state would be say n into nu, with nu being the natural frequency. Now, then we evaluated mean energy of one oscillator. That mean energy of one oscillator, in that calculation we define something called as the partition function, which we require later on in calculating Helmholtz free energy. Now we defined energy for the entire system. We mentioned that when the atoms come together, there will be some other interactions. That form of interactions is captured by potential energy function phi. There will be some ground state energy, and then there will be some oscillator energy. So because you have a large number of atoms, you calculate the mean energy of one oscillator and multiply it with the total number of atoms. That will give us a very good estimate. Now we moved on, we used an equation from statistical mechanics. So we directly are using it. We are not looking at that equation in detail separately. We looked at Helmholtz free energy calculation. From that, we also looked at how pressure is defined. So we use that to evaluate pressure for the entire system, which again includes your potential energy term, your ground state term, and your average energy term for each of the very large number 3n oscillators, where n is a very large number. Then we in the process of differentiating the Helmholtz energy with volume, we change the differentiation to frequency nu and define a Grunew's constant gamma I. So that is the Grunew's constant. That constant, we argue that we assume rather, not argue, we assume rather that it will remain same throughout all my 3n oscillators. That allows me to isolate right pressure as a function, as a derivative of potential energy, and a function of the Grunew's constant, volume, and the total internal energy of the system. We ideally we can calculate this equation at 0 Kelvin, because at the very beginning what uh, sorry, because at the very beginning we have looked at the energy versus distance plot that is theoretically calculated for 0 Kelvin, but we argue that uh, we can not argue, rather we assume that there will not be a large change in the energy versus distance plot at the very beginning of this uh, equation, the Condon-Morse curve. Because if assuming that holds, assuming that there is no large change, we can write this a similar equation at uh, another state P and E, and as again this requires your volume to remain constant. So from that we can write differential of pressure is gamma by V times differential of internal energy. Now we did some more jugglery in that equation. We calculate this. We calculate this Grunasa constant gamma in terms of partial derivative of pressure with respect to energy in for constant volume, and then again playing around with our thermodynamic state variables PV and T, we end up with an equation that looks like it gives us a good approximate for gamma. And again, if there is not much change in your alpha, CV, and compressibility values, K, kappa, you can say that the ratio gamma by V for two different states should be same. So that argument basically leads us to evaluating gamma for one given example for copper. There is also an empirical relation that I mentioned here, which we verify using which we estimate gamma 2s minus 1. That has been for a large number of materials. We have evaluated our equation of state constants S, and then they have seen that this gamma is equal to 2s minus 1 rule applies, matches, at least gets us in the proximity of the actual gamma. So a lot of steps, a large number of assumptions. I would urge you to go through this once again, even if suppose you do not necessarily, even if suppose you directly take the pressure and Helmholtz free energy equations as given, just looking at all the assumptions and how we flow through it would be a good idea to uh, understand this properly. Okay, because the way we derived this, right, we did not necessarily assume that my atoms are closely packed or they are in a particular configuration. This equation can be extended to powdered materials as well. We'll come to that in a moment, but first we'll quickly look at mixtures. So, so if you have like a single phase alloy, then you could have say two atoms A and B coming together in a particular arrangement. So here, apart from all the terms of free energy, so additional terms being mixing free energy and configurational free energy. So what do I mean by single phase alloy? I would have say something like the vertices of, assume that these vertices of cube are one kind of atom A, and inside I have another atom B. All A is vertices. Right? How A and B come together, when they come together, that will have some effect on the potential energy function that we already discussed. Between A and A, it would be some sort of like it would uh, if you have only atoms of A, you can more clearly define some sort of potential function. But if you have say atoms B interspersed between say a matrix of atoms A, depending on how the B atoms are placed in the neighborhood, you'll have some additional term associated with the mixing free energy. And if how exactly they are placed, if there is a repetition or so, if it's homogeneous both macroscopically as well as microscopically at the largest levels as well as the tiniest levels, will also have the configurational free energy based on how B atoms is placed, whether suppose it's at the center or center of the cube or face, something like that. An easier one would be say like a two-phase mixture. Again, easier is a relative term. You have, suppose, A and regions of B mixed inside A. Now this thing is a little, this thing is, if you can see this AB interface, right? This interface, again, if we assume perfectly bonded interface, which is what we had in the plate impact, parallel plate impact, you have those two conditions, right? So you have got pressure equilibrium and displacement continuity. You remember, between A and B. So if my Huguenot pressure by V naught A, suppose I can write my equation of state as this, and for B I can write equation of state as, right. So these are my equations of state. I have pressure equilibrium, so whatever Huguenot state A achieves and B achieves, they will both have the same pressure. Again, this is a complex scenario. Normally, you would also have something like temperature gradients around interface. We are we have not taken those into account. So this, again, like in both cases, whether it's a single phase alloy, again, in both cases, whether it's a single phase alloy or a two phase mixture, your actual calculation becomes much difficult. You may go through a thermodynamics based route to get some sort of idea. But a very simple rule that is often used to arrive at a initial point, or I guess, like a, think of it more like a calculated guess point about the region where what, how the equation of state would look like for the two phase mixture. You basically do mass averaging. So C naught is equal to MA C naught A plus MB C naught B S naught, sorry, S is equal to MASA plus MBSP, and rho is equal to MA rho naught A plus MB rho naught B. So you use this to evaluate, find equation of state for the two phase mixture. So we are talking about two phase mixture here. US is equal to C plus SCP. So this is a good approximation. So unless you are like really interested in getting the calculation very right, you can use a simple mass averaging technique to evaluate equation of state for the two phase mixture. If we want, suppose like we take an example, again this is theoretical, I don't know this. Suppose you have something like 90% copper and 10% iron as a two phase mixture, then if I have to find EOS, my C would be say zero point 0.9 times copper, it is 3940 plus zero point 0.1 times 357. Similarly, my S would be zero point 0.9 times 1.49 plus zero point 0.1 times 1.9. So, like a simple mass averaging we can do to evaluate to get an estimate for speed of sound and the coefficient in the uh, Huguenot equation. Okay. think I'll, so I think we are now on the last part. So now the final part is how do we evaluate equation of for today's week. Sorry, the final part for this week rather is to is to find an equation of state for powdered materials. So we first consider the case of solid. So you have got again four equations, three conservation equations and one equation of state. You can write rho times us minus up is equal to rho naught times ush. This is mass conservation for solid. Momentum conservation for the solid would be rho naught ush uph, and energy conservation would look like half ph v minus v naught minus v, and assuming like the initial state to have form the reference for our initial state. So that is important. And this is my equation of state. So assumed form of us for solid. ush is equal to c plus s into uph. So for solid, suppose like you have nickel, right? For nickel, you can evaluate what nickel, solid nickel is solid nickel metal. You can evaluate a linear relationship between shock wave velocity and particle velocity. We have already seen that linear equation of state works well for metals. So that becomes our starting point. Another is the powder. The second part is the powder. Mass balance would look like rho double naught us. This is for the powdered state. Next is pressure rho double naught USUP. Okay, this H refers to H would refer to the solid state, and energy is half of E times B double naught minus V. Okay, we are missing one equation, so that is the equation of state. Here we'll use the, as I mentioned, we can use the Mead-Ronessa equation of state because we have not assumed any particular form of the system, how the atoms are arranged in the overall aggregate system with capital N atoms. So that would be gamma by V E minus EH. Okay, so by combining this, I'll just write down the final equations in the interest of time. I think these are easily solvable. You can do so by combining this, and this. You get an equation which looks like pH is equal to C square V naught minus V upon V naught minus S V naught minus V, the denominator whole square. Using this equation with EH and E and EOS powder or Mead-Ronessa EOS, GES, right? Using this energy equations for powder, for energy conservation equation for solid for powder, as well as the Mead-Ronessa equation of state for the powder, you end up with a pretty large equation that looks like 2V minus gamma V naught minus V C square V naught minus V upon 2V minus gamma V double naught minus V naught minus S V naught minus V whole square. So PV for the PV for the powder, we can determine. So the shock state of the powder P and V, we can determine by using V naught. We know V naught for the solid. We know C and S for the solid. We know, so this is solid. And we know gamma for the powder. So this gives us a pressure volume relationship, which forms our fourth equation for the powder. Sorry, which relates powder PV to your uh, solid parameters. Again, we further end up with different relations between, say, pressure and particle velocity, as V is V00 minus UP square by P, which tells us that as the particle velocity increases, my shock state volume for the powder, which is capital V, is less than my initial unshock, which was V00. So as shock as the shock wave pressure would increase, my particle velocity would increase, and that would lead to powder compacting, so to speak. Another is US is equal to E double naught root of E, E double naught minus V, and particle velocity is P times E double naught minus V. So if I plot this for the pressure versus relative volume, for a solid, my line would look like this. Solid, whereas this is how it would look like for different levels of porosity. So suppose this is 90%, 80%, 70%, 16%, 60%, 50%. So my Migronessa equation of state for powder ends up predicting that for same pressure, P volume increases, volume which is V increases as porosity increases. This is 1, this is 0. For the same pressure, you can see that as the porosity increases, you will have a larger volume. Another thing that this ends up giving us is that I'll just write it qualitatively. So you can obtain high internal energy states in powder, which is not normally seen in, which would not be easily achievable rather in solids. And another thing is that you also see high attenuation. You can also compaction. So powdered materials study. So from this we see that we'll be able to achieve high internal energy states which are not normally seen. There is also, as a shock wave passes, there is also attenuation. So and you could also lead to compaction. So we have seen that high amplitude shock wave can bring the particles together and cause fracture between them to take us from a powdered material into a monolith, which has which is basic which can be used industrially in manufacturing. Okay, so I think this is the gist of powdered materials. I think we are out of time today. If you want, I can upload this derivations for the powdered material separately on the discussion forum. Uh, I think I at least hope that some of the concepts might be clear, especially those related to Migronessa equation of state. Do you have any particular doubts in what has been discussed? If not, then we'll close. Sorry, today went a bit longer than usual, but I felt that the Migranesa was particularly important to go into detail. Okay, if there are no doubts, then we'll close this lecture. Thank you for attending or watching it online. I'll see you again in the next one.